Okay, so morning, thank you for joining. And so what we are going to talk about today is going to be a little bit lateral to the concept of the Bayesian optimization and active experiment, but nonetheless absolutely essential for understanding things like deep kernel learning and generally how to use the machine learning methods in either practical or theoretical situations. This topic is the concept of the autoencoders and variational autoencoders, and very closely related definitions of things like encoding, decoding, latent representation, latent images, and so on and so forth. So let's start from the very beginning. So what are the variational autoencoders? What are the latent distributions? What are latent representations? What does the disentanglement of the representation means? And why do we care about the invariances? So first of all, I mean, all of you are familiar with the neural networks in some form. And the autoencoder is a special type of the neural network architecture. So the best way to represent it is to have two funnels connected with their narrow sides end to end. So imagine that you start building your network by creating the input layer that adopts your data. So it has the same dimensionality as your data object. Obviously, your data object can be image, it can be spectrum, it can be the three-dimensional volume coming from videos or the hyperspectral data. It really doesn't matter. So once you start with this object, you set it down through the set of the convolutional filters. So what they do is they will reduce dimensionality of the object. Typically, after a few convolutional filters, you will send it to the one or two fully connected dense layers. And in the end, you will end up having a low dimensional latent space. So this is essentially a bottleneck through which all the information has flowed. Again, as I mentioned, the structure of these funnel layers can be anything. It can be convolutional, it can be a classical dense perceptron layers, it can be graph network, so anything whatsoever. The only key part is that you start with the high dimensional data object and you convert it to a very low dimensional representation. So this part of the autoencoder is called encoder. So then what you do is you take this latent representation and then you try to deconvolute it back to the original object. So you start with the increasing the dimensionality through the set of dense layer, and then you start to go through the deconvolution layers. When you train the autoencoder, essentially what you try to do is to minimize the difference between the input image and reconstructed image. So by itself, it sounds maybe a little bit stupid. So you have the neural network architecture that basically tries to reconstruct the data from itself, nothing else. So the question is, why is it useful in the first place? And it turns out that the reason why it is useful is because once you have the data, you basically force it to go through this bottleneck of the latent layer. And in doing so, your reconstructions adopt some interesting properties. And also, you're able to introduce some very interesting operations with the data. So let's go through them one by one. So the first start of the process, let's assume that we develop the autoencoder for the image data. And we start with the prototype MNIST dataset just because it is very convenient. So we start with these objects, which are 28 by 28 pixel images. So it's 756, if I'm not mistaken, dimensional data set. And you downsample it down to the two-dimensional latent layer. So 2 dimensions is very convenient because in this case, we can represent the latent spaces just in the image. In most cases, we, of course, play with the number of the latent dimensions. We can have 2, 3, 4. If we have work with the very high dimensional data, we can go to 100 latent dimensions, but usually it is much less than the data anyway. But for the purpose of illustration and practically working with the simple imaging data, 2-dimension is actually not bad. So what we do is that we start with this data set. We have all 50,000 images in the MNIST, and we train this autoencoder, and then we try to see what is the relationship between the image and the latent vector. So again, latent vector is 2-dimensional. The first component is Z0, first latent variable. Second is Z1, second latent variable. So we get two numbers, Z0 and Z1, out of each image in the MNIST dataset. Once we do that and we plot these images in the this latent space, you can see that all the ones are sitting in this part of the image. All the 7s, and sometimes mixed with 9s, sit in this part of the latent space. All the 0s are sitting in this part of the latent space. So what it immediately tells you is that the latent space representation preserves some relevant information about your original data set in some simplified form. So this is already very useful. However, we looked just on the encoding part. So let's look what we can do with the decoding part. So if we do decoding, we pick a point in the latent space, we send it to this part of the autoencoder, and we try to reconstruct the original image. But here the interesting things happen, that we are not bound to take the point in the latent space that has a corresponding object that we train on. We actually can take any point in the latent space and try to decode from this latent point. So this is so-called the latent representation. So imagine that I take my latent space, I sample it on the uniform grid, and then I decode the object from each point. And then I plot them in the same coordinate system as my original latent space. So lo and behold, you start to see a very interesting picture that this part of the latent space has 1s, this part of the latent space has 0s, this part of the latent space has 7s. That makes a lot of sense, because if you look at the original latent distribution, you see that 7s are here, 1s are here, and 0s are here. Now, the important thing is that some of these objects were never a part of the original data set. So we essentially used a data set, an example, and we generated the new objects that look exactly like that. So this is why the autoencoders are called a generative model. They allow you to create a new in-distribution data. And obviously, the most famous example of the generative model now are large language models. They obviously use a little bit more complex technology than autoencoders. They're based on the transformers. But autoencoders were one of the first examples of the generative model. So interestingly enough, if you look at this part of the latent space, you see that the objects here are not any kind of reasonable number. So why is that? Because here there were no original data point, and basically the autoencoder tried to interpolate between the 0s and 1s. And whereas you can interpolate between, for example, 4 and 9s, 4 and 9 look essentially the same, it's just the shape is slightly different. You cannot interpolate from 0 to 1. These are very, very different. So as the result, the autoencoder generated something that is not physical. So this is a very simple example of how the autoencoders work, but it's already very important. So it gives you an example of what is the latent distribution, what is the latent representation, and it shows you that autoencoders allow you to generate new data and interpolate between the existing data sets. And sometimes this interpolation is physical, like between the 9s and 4s, and sometimes this interpolation is unphysical, like between the 0s and 1s. So what's very remarkable is that these properties of autoencoders would be the case would also hold for much more complex data sets. So how important are the autoencoders? So one of the legendary figures in the field of machine learning is Geoffrey Hinton, who is one of the fathers of the machine learning, along with the Jan LeCun and several others. So if you look at his H index, it's something like 200,000 citations, with some of the papers that have been cited 130,000 times, so rather impressive. And one of his most cited papers is actually reducing the dimensionality of data with the neural networks. And this is actually the paper about the autoencoders. So this is 20,000 citation, which would be impressive for any field. So what can we do with autoencoders? So one kind of how can we use them other than encode and decode data? So one of the classical ways to use them is for denoising. So imagine that I have my autoencoder and train it on the subset of the Maniz data set. So these are training examples. Then I give it the new example, but I train it not on the image to image. I take the images, create the noisy images, and then I train it to denoise the image. So the encoded images are noisy, decoded images are not noisy. And then if I give the examples of the noisy images that the autoencoders have never seen before, it will be able to decode, to denoise them. This is a very impressive capability. The reason why it works is because once you send your data through this bottleneck layer, it preserves the characteristic and repeating features of the data, and it rejects the noise. So once you start to apply it for the noisy data coming from the same distribution, you can decode it very effectively. So the concern here is that it has to come from the same distribution. So there are a lot of attempts to use the autoencoders to analyze spectra or images in microscopy or any other physical measurements. The danger here is that if your training set contains certain features, but this feature is not present in the real data, then the autoencoder will try to reconstruct it anyway. So this is a usual problem with all the neural networks and something to be aware of. So interestingly, autoencoders can also be used to reconstruct the colors of the image. So if you train on the pairs of the grayscale and color images, you apply it to the new grayscale images that should be a part of the same distribution. Again, you can polarize the images, but the problem would be that it has to be for the same distribution. For example, if you train your image on a network on the image that has something unusual like a red sky, and then you make it gray, and then you try to reconstruct the sky color, would not be reproduced faithfully simply because it is not in the training distribution. So again, very important consideration to be aware of. So this is how the autoencoder works. So it turns out that the classical autoencoder architecture is a little bit too brittle for many applications, meaning that the large parts of the latent space are actually unphysical. So the way autoencoders were improved by transition to the variational autoencoder. So if you just use this technology, it doesn't really matter how it works, but it actually is a technology which is very recent. So the variational autoencoders have been developed less than 10 years ago. So it's a very new technology in the computer world. So the only thing that you need to know is that the VAEs use the reparameterization trick in order to sample from the latent space. Other than that, they can be used for the same tasks as the normal autoencoders, but they have a much better behaved latent space, which almost never contains the unphysical regions or have the unphysical regions compressed to a very small part of the latent space. And they also have a unique property that is called the disentanglement of representations. So this is something that first manifests in the variational autoencoders, but it is also exceptionally important for the deep kernel learning that we are going to look at next. So let's look at how the variational autoencoders train and what the disentanglement of the representation is. So typically when we work with this type of applications and kind of try to understand how they work and develop intuition, we use our data with the ground truth. For example, for the mnist image, the ground truth is the fact that each image is associated with a known digit. So one way how we can explore how the autoencoders work is by use the digit number, so 0 to 9, as the color in the Latin space. So in principle, the autoencoder does not know what digit it is. It's given a set of objects and it tries to somehow arrange them in the Latin space. However, for us to understand how this process works, it is very illustrative to observe how the labels are distributed in the Latin space. Because if we see that different labels are well separated, we would be able to say that in this case, autoencoder can be used to cluster the data. If the labels remain mixed, we know that we have access to the ground truth, so we see how the algorithm behaves. But in the real world, we would not be able to separate these labels. So it's a very good monitoring signal, and it also kind of aesthetically pleasing. So the pictures of the training of the autoencoders in the Latin space and then the Latin representation is actually pretty cool. You basically see how the network learns to reconstruct and understand the objects. So this being said, let's look at what is the disentanglement of the representations. So this is probably one of the most important concepts in the whole field of the generative models, which can be used in a very large number of applications, and which actually does not have a rigorous definition, at least not to my knowledge, and not until maybe half a year ago. So maybe somebody is working on it right now. So it's one of those things that, as I said, also doesn't have an analogs in the normal experimental physics world, but it is very easy to illustrate. So imagine that we kind of move ahead a little bit, and rather than looking at the normal variational autoencoder, we are going to look at the conditional variational autoencoder. Conditional autoencoder means that now we essentially create the Latin space for each of our classes. So we train it not only on the images, but we also train it on the images with the appended class label. If we do that, so technically it is done by concatenating the class label at the dense layer and in the before the latent and then the dense layer at the output. But the result would be that we essentially create the latent space for each class. So notice an important thing that conditioning can be discrete. So you provide the class labels, but conditioning variable can also be continuous. So it is a way to structure the way the autoencoders work. So anyway, in this case, I use the very simple Keras autoencoder, which I build and train it on the mnist dataset with the classes being available. And I also, as a result, I get the latent space for each of the digits separately. So this is, in our previous example, we have the latent space that is shared between all the digits. And correspondingly, what it tries to do is to put different digits in different parts of the latent space. Now I give each digit its own latent space. See what happens. So if you look at the 6s, 7s, 8s, and 9s, you will see that they have the same trends in all the latent representations. So for example, if you move in the Z0 axis from negative to positive Z0, so here 6s, 7s, 8s, and 9s are short and chubby. Once you move to the right, they become narrow. At the same time, if you move top to bottom, you see that here they're all tilted to the left, and as you move down, they become tilted to the right. And this behavior is the same for all our digits, all 6s, 7s, 8s, and 9s. You see that they are kind of almost similar. So this is what the disentanglement of the representation means. The data has the factors of variability, which is in the handwritten digits, is essentially the tilt and the width of the writing. And the variational autoencoder disentangles the data in such a way that latent variables become associated with these factors of variability. This is exceptionally powerful property that is almost unused for now in physical sciences, but is used very, very broadly in the application of the machine learning for all kinds of technologies like Facebook, TikTok, and whatever. So many of you probably played with the apps when they take a picture of your face, and then you can see how you would look 10 years earlier, how would you look, say, with or without glasses, how will you look if you add a mustache or something like this. So the way it is done is that people find the relationship between these attributes and the latent variable, and then they shift in the latent space. And then remember that autoencoder is a generative model. If you want to say how would my handwriting look if it was a little bit more narrower, all you have to do is to encode the letter, shift it in the latent direction corresponding to the width of the writing, and then decode it back, and you will see how your handwriting will be if you were writing in more narrow way. So there are many other ways how this capability can be used for text analysis and what's not, but this is what it means. So combination of the fact that autoencoders allow you to disentangle representation and the fact that it is a generative model, meaning that you can shift along one of the representation and then generate the image, makes it a super powerful technology. So in fact, quite a lot of work I've done was dedicated on using the autoencoders for understanding the physics of materials, and you can read about it on the archive. But let's first look a little bit about why we need to expand upon the autoencoder concept and start to build invariances of the system. So let's start with a very simple example of the, so MNIST is a good data set to play with, but it's a little bit too complex because it has 10 digits, so it kind of makes bookkeeping somewhat messy. Let's come up with the easier data set, which is just the 4 hands of cards. So the diamonds, hearts, bikes, and clubs. And let's assume that we generate several hard data sets, where one is just a original data set. One is the data set when we apply high strains to the high shears to the data. So you see these are all normal. This clearly sheared in the different directions. And we add a little bit of the rotational disorder. So we augment the data via the rotation. Then we make a third data set where we apply high rotation and low shear. And of course, as you can guess, the fourth data set would be high rotation and high shear. So why did we do that? So we did it because it is always a good idea to work with the synthetic data sets first and understand how the machine learning algorithms work using the synthetic data sets where we know the factors of variation. So in this particular case, the factors of variation is the obviously hand, and we add 2 more factors of variation, which is the rotation and shear. So let's see how it works. So the first thing we do, and we'll go through this first in the PowerPoint presentation, and then we are going to play with the notebook that actually does this analysis. So the first thing we do is we generate a data set. In this case, it's about 4,000 pictures. Then we take few examples. So this is the examples of the data. So this is what happens if we send this data through the variational autoencoder and make the latent representation. So it's not an ordering, now it's a decoding from the latent space of the encoder. And you can see that it actually behaved exactly the same way as our MNIST data set. You can see that the clubs are sitting in this part of the image. You see that diamonds are sitting in this part of the image. You see that hearts are sitting in this part of the image. Pikes are sitting in this part of the image. So we cannot say that the we cannot say that the latent variables in this case have any particular meaning. So if you go in this direction, it is global meaning. Locally, we can always define what it means. So locally here, Z2, if Z1 is fixed for -1, corresponds to transitions to from diamonds to pikes. Here, it will correspond to transition from pikes to clubs. But this is not a global matrix, so this is a local matrix. So one useful thing to know is that, to remember, is that the disentanglement of representation allows us to identify the factors of variability linearly only locally. Sometimes it is possible to do it globally, and then we are a completely different ballgame, because then we introduce the physical meaning and capability to extrapolate, but generally it's not the case. So only local linearity works. And you can also see that some of the objects that are on the boundary between two different types, they are kind of imperfect, meaning that in this case, generative model failed. So there is a poor, it tried to reconstruct something that interpolates between the diamonds and pikes, and this is not perfect. So this is another example of the failed reconstruction. So another important thing is that in this case, we reconstruct 10 by 10, but by property of the generative model, we can make it much denser. We can reconstruct 20 by 20, 100 by 100, I mean, as much as we want. And then, of course, we will see these boundaries between the real and the objects and the unreal objects on the boundaries much better. So now let's look at how the latent representation, latent distribution of this data set look like. So this is the case when we have low rotation and low shear. And this is the encoding in the latent space, so latent distribution. And we color our object. So each point here is as one of the cards. The color of the point is our label. So let's choose the suit as a label. So they can be 0, 1, 2, 3. So we have 4 suits of cards. We have 4 labels. See what happened. If we take our data and encode it in the latent space, you can see that it formed 4 well-defined manifolds. These manifolds are not linear. They kind of have some sort of weird wiggly shape, but each manifold corresponds to a suit of a specific suit. So these are whatever diamonds, these are hearts, and so on and so forth. So in this case, we see the colors, so we have access to ground truth labels. But imagine that you have this data and you have no colors, so you don't have access to the ground truth. If your data forms 4 separate, well-separated clusters in the latent space, you would be very easily able to say that this is group 1, this is group 2, this is group 3, and so on. So we would be able to use the autoencoder in order to represent this data and cluster it in the individual clusters very cleanly. So obviously, practically, if you want to do it, you of course cannot use the PCA or linear method, but things like dbScan or TSNE or UMAP applied on top of this data set will allow you to very clearly separate it in 4 groups. So now let's play with the other labels. So remember that we had 3 factors of variability. We have the suit, we have the shear value, and we have the angle value. And in this case, we have 3 factors of variability, but we try to squeeze our data in the 2-dimensional space. So see what happens. This is obviously the strongest factor of variability in this case. If we look at the data and use the angle as the color, you can see that the angle changes across the manifold, and it does so in a predictable manner. So notice that all of this start here, they are all -10 degrees. Then if you move across the manifold, it becomes 0, then it becomes +10. Interestingly, this one starts as +10, and then it kind of goes to negative. So what does it tell you? It tells you that if you look at this latent space, you can clearly see that here you will have the negative angles of rotation. Here it would be positive, and here it would be again negative. We don't have the objects everywhere in this space, but we can clearly see that if we sample at this location, this is how the disentanglement of representations work. Finally, if we look at shear, situation is very different. So if you use the shear as a label, you can see that colors are kind of mixed in most places. If you look very carefully, you can see that when the manifold stops being one-dimensional and tries to expand to become two-dimensional, you can see that shear becomes a color gradient, which is orthogonal to our angle. So basically, within each manifold, the variational autoencoder tried to disentangle the angle and shear. It cannot do it because we cannot disentangle three independent variables in the two-dimensional space, but it really tried to. So notice that we spent quite considerable time going through this process of encoding, decoding, and disentanglement. And the reason why we have done it is because this is really as I mentioned, this is a foundational concept for understanding how machine learning works and why machine learning works in general. And this is something that we are going to use in many applications down the line. Also, this is how you use the same logic to study the physics of the system, right? When with the cards, we had access to the ground truth, and we know what the factors of variation are, but we can apply the same approach to the unknown data, and then the latent representation will suggest to us what is the factors of variability, and the latent distributions will tell us how our data behaves and kind of how these factors of variability are statistically represented. Okay, let's do the next step. Let's see what happens if we take the data set and we increase one of the factors of variability. So in this particular case, we have the low rotations, but we have the high variability of shear. So see what happens. So in this case, our latent representation, if you squint right, you can see that we see the systematic change of the way the objects are sheared in the latent space now. So it's sort of difficult to see it in the latent representation, so we can look at the latent distributions, and lo and behold, we have a very beautiful picture. So this is our latent distribution. So we again playing the same trick. We impose the labels, which are the suit of card. We impose the label, which is shear. We impose the label, which is angle. See what happens. In this case, we no longer have a one-dimensional manifold. So our data set has significant variability. So now it kind of wants to occupy a two-dimensional part of our whole latent space. We can see that this kind of clouds corresponding to suits are still separated. So you can see that very well that the colors form the individual islands. Now, notice one very important thing. So you see that the cloud of points corresponding to the label number 1 is actually not continuous. So this is one subset, this is another subset. If we did not have access to the labels, we would not be able to say that this and this are the same at all. As it is now, this is not a simple clustering problem. So if you have access to this data and imagine that the labels are not there, you will not be able to, it would not be a trivial problem to separate it into groups. Practically would be able to do so with a t-SNE or UMAP, but in this case, this group would be separated, but it is very likely that this cluster and this cluster would be separate, not identified as the one. These two clusters would be identified as separate as well. So it's a kind of good exercise to take the notebook that I will share and simply try to apply the t-SNE on the latent representation. But anyway, since we have the ground truth data, we can kind of enjoy the show. This is how the shear labels are distributed. Notice that what happens in this case is that the shear tries to change monotonically from this part of the latent space to this part of the latent space, but this is clearly not possible. So you see that there is some systematic behavior here, but this region is the cluster of the negative shears, and then they become large here again. So it's tried to disentangle, but given the limitation of how much real estate we have in terms of dimension, it doesn't work very well. But this is what happens with the angles. So in this case, you can see that each of the manifold clearly has the angle gradient, and you can see that locally the direction at which the shears change and angles change are orthogonal. So locally, we disentangle the shear and angle as orthogonal factors of variation. So it doesn't do us much good because we don't have access to this type of things. We don't have access to the ground truth labels in the real world scenarios. However, this is the case where the representation learning comes into play. So basically what the representation learning is the how you modify the variational autoencoders in such a way that the factors of variability are partially controlled. So for example, an example of the representation learning would be for me to say that, you know what, I want the angle to be aligned with the latent variable z1, and then the shear would be also much better behaved because it always tries to be perpendicular to the angle. What you would see in this case is then the suits would be distributed much more randomly. So there is no free lunch. But anyway, let's go to the next example. Now let's take the example of the same data set when the rotations are much higher and the shears are lower. So if we do that, this is what happens. So in this case, our manifolds are now still one-dimensional, but very, very zigzaggy. So you can see that they kind of try to fold on themselves in the latent space, almost as if we are trying to mix the liquids together. And then if you look at the behavior of the ground truth labels of shear and angle, you can see that the angle start to change monotonically across this manifold. They're complex, but you can clearly see how the color gradient behaves. You can see that the regions with the same angle are close to each other. So these are two different suits, but the same color, same angles try to be concentrated in the same part of the latent space. So it tries to be locally smooth. And kind of, you can see that shear in this case don't have a chance. So basically all the shear labels are mismatched because there is no second latent dimension for them to disentangle it. The final example is, let's have the high rotation and high shear. So there is a large variability in the data. If you look at the latent representations, you can already see that reconstructions are not super good. So we are trying to encode too much in the latent space, and it kind of doesn't work. And correspondingly, the results of the deconvolution are kind of very weird. So you see that the suits are kind of mixed. Shear is, I mean, it's still locally smooth. Angle is kind of tries to be ordered. You see that the angles change across the latent space, but it's not perfect. So the best analogy you can, so this basically illustrates this concept of the manifold and on which machine learning is built. So if you imagine the general object that has image that has objects like whatever, cats, dogs, whatever, choose your favorite objects, geckos for that matter. So the image has a very large dimensionality. However, in this total enormous image space, there is a manifold corresponding to the cats or dogs, and this manifold would have much lower dimension. The whole idea and the reason why machine learning is possible is because it more or less successfully discovers this manifold. Whatever we can do to make the manifold smoother makes our learning more efficient. So effectively, you can say that when the manifold behaves like this, you learned well, and when the manifold looks like this, you learned sort of less well because the same object now split into groups. So the problem is that a human brain is obviously limited to a relatively small number of dimensions. So we can think in 2 or 3 dimensional, rarely 4, but probably not more than that. The manifolds that exist in the real world are much higher dimensional, but their dimension is much lower than the dimensionality of the embedding space. So when we look at the simple data sets like CARD, and we use the example with a few factors of variability and encoding in the 2-dimensional space, we basically try to develop the intuition of how these manifolds may look like. And we also learn that they have a useful properties. This for the disentanglement of representation, these properties are local, and if we are lucky, then they will expand to the global case. Now, this being said, a very important question becomes, can we make our learning better? And the learning becomes much better if we actually know one of those factors of variation. For example, in this data set of the cards, our factor of variation that we may separate physically is rotation. So for kind of incorporating it, we use a slightly different approach, which is called the rotational invariant autoencoder. The way it's going to work is it's going to take the data, still find the latent vector, but it will try to separate the rotation of the object as a separate physically defined factor of variability. So rather than saying represent the unknown system as the latent variables and we don't care what they are, we modify the architecture of the network in such a way that we represent the system as the latent vector, vector and angle, which have a well-defined physical meaning. So there are, of course, other factors of variability we can introduce, like shear or strain. Of course, it can be taken much further. So if you have an idea of how to define the known factor of variability, we can introduce it in the variational autoencoder structure one way or another. So it gives us a degree of control of physics of what goes on. And interestingly enough, if we start to add this rotation of the factor of variability, so we can start with the same data set with low rotation and low shear. We can try to encode in the latent space of rotation invariant autoencoder. And in this case, we have no longer two latent representations. We have three because we have Z1, Z2, and the angle. So let's see what happens. So if we do that, then our suits, they're as you see, the manifolds are now more like essentially points. So they become a very short segments and very well separated. You can see that if we use the shear as the ground truth labels, it changes systematically across this across the whole manifold. So now shear is disentangled. So now we no longer have a ground truth. Now we have an angle as a separate latent variable. So what we can do is we can compare the angle that the autoencoder gave us with the ground truth angle. And you can see that it didn't find it precisely. It found it down to the offset, but the angle changes from minus 0.4 to 0.4 in the ground truth. You can see that for all this data, it basically changes from 0.5 to whatever, 0.9. So basically, we reconstruct the angle down to the random offset, but the trend is the same. Great. So can it work for a kind of different combination of the rotation and shear disorder? Of course it can. So if we go for low rotation and high shear, you can see that now suits are linear. The shear is still the disentangle across the manifold, and the angle is kind of reconstructed okay. There is a noise, but it is it's not bad. We still can see it. So compare it to the case when we did not have rotational invariance. So in this case, our manifold looked like this. So you see that here, our latent distributions are essentially two-dimensional. It's a point of cloud points. Once we allow the rotation to be a separate variable, they become lines, and the shear is now disentangled. So once we give this system more degrees of freedom to separate the factors of variability, the answer is simplified. And that's actually another very interesting thing for use of the autoencoders in the real world scenarios, which is kind of took us some time to figure out. So when people in the computer science community work with the VAEs, they have a problem. Apologize. they have a problem of the representation collapse, meaning that they take their data, they try to encode it in the latent space that has, let's say, 5 dimensions, but the data decided to form a 2 or 1 or 0 dimensional manifold. So it didn't spread to occupy all the latent space it was given. It decided that it is low dimension. So from the point of view of the computer science, that's a problem. From the point of view of applications of variational autoencoder in physics, this is actually a discovery, because the collapse of the representation happens if we know all our factors of variation. So the data that does not have factors of variation becomes a single point in the latent space. And if that happens, that means that we already know the factors of variation. So from physical physicist perspective, this is absolutely awesome. Okay, let's look at the 2 more examples of the same data set. So high rotation and low shear, beautiful result. So see what happens. We separated our data in the clusters. So they're almost like points, meaning that suits is the primary factor of variation. Within each of this localized distribution, shear changes uniformly. So we disentangle it. Notice a catch. So remember that no machine learning algorithm is perfect. We expect that all these data sets have continuous factors of variability. But much like this example, where the latent distribution for points corresponding to the same hand got split in 2, the same type of phenomena happened in this case. So as you can see, the group corresponding to the label 2 actually become 2 groups. So they were not able to kind of coincide. And you can see that our reconstructed angle have a discontinuity. So if the variability of the data is relatively small, you can expect the clean separation and clean discovery of the factors of variation. If the variability is large, sometimes of finding this type of false minimum actually happens. To some extent, it is possible to control it through the training of the autoencoder. So we, of course, are not going to go into that, because that's a kind of separate area, and it's digging pretty deep into under the hood of the variational autoencoders. But sometimes it's possible to tune this process by essentially balancing the reconstruction loss and the KL loss during the training. So, but again, it is more engineering than science at this point. Sometimes it works, sometimes it doesn't. And finally, let's look at the high rotation and high shear. So in this case, it still worked reasonably well, but notice that now we still have a good separation of the latent distributions, but the clusters are kind of, I mean, they cannot cross because the objects are different, but you can see how they kind of are forced to coexist in the same low dimensional space. And the disentanglement of shear is still there, but it is local. Angles can be reconstructed, so that's not bad. Now, so this is something that this is the illustration of the classical and rotationally invariant autoencoders. So as I mentioned, we have the opportunity to have the autoencoders that come also with the translational and shear and scale invariance, and I'll show you the example in the notebook. But before we go to the notebook, let's have a brief look at the other colors of the VIEs. So what else can they do? And I'll show you a few examples of how the VIEs can be applied to the real world problems. So as you can imagine, the interesting science is all about the real problems and not the training set. So first, and then another important thing is that VIEs have been used for quite a while now. So I'm currently in the microscopy conferences in Minneapolis, and there are quite a few work where people use variational autoencoders for image analysis, for spectrum analysis, for the denoising, and so on and so forth. However, when we talk about the semi-supervised conditional or joint autoencoders, to the best of my knowledge, at least in the areas of the imaging and experimental sciences that I'm aware of, the number of publications in this area is either zero or close to that. So these are the technologies that are out there that are available in the form of hopefully easy to use code from our group and from many other groups. And to be honest, there are quite a few textbooks that actually show you how to build the conditional or joint VAE. And for the time being, they haven't really been used much. So the reason why it is the case, at least in my assessment, is because it takes a little bit of effort to understand what type of problems they can be used for. So let's have a look. So if we don't know anything about our data, we use the simple variational autoencoder. So we start with the data, we dump it on in the autoencoder, we get out the latent representation. The autoencoder can be simple, it can have the invariances. This all means that it affects what types of the how we control the latent variables. So they can be anything or they can have physical meaning. Now, there are several more types of autoencoders when we know something about the data. So a simple example is the conditional VAE. So this is used in cases when we know the classes of the data, as I've shown you with this example of the MNIST data set. So each image has a class label. That means the class label is known, which basically means that we can create a latent space for each class. And it also means that we disentangle representation of the data for each class separately, but in the same sense. So the latent variables will have the same meaning for all the classes. So if the factors variability are known but continuous, then we can use the conditional continuous VAE. So in this case, we basically condition it on the known data. It can be scalar, it can be vector, it doesn't matter. So in this case, we kind of create a latent space where some of the directions are latent variables that the autoencoder discovers, and some of the dimensions are the continuous vector that we actually provide. So this is one of the simplest form of the representation learning. Now, the two more classes of the autoencoders are the semi-supervised VAEs. So imagine that you have labels for some of the objects, but not for others. So what the semi-supervised VAE will try to do is to identify what would be the label for the unknown object. This is a very, very powerful approach because one of the ways we can use semi-supervised VAEs is imagine that you have a lot of experimental data, and then you have labels, either manual or coming from the published work, for some of these data points. So then you can analyze the data to disentangle the representation and find most likely values for other objects. So the fact, given that the semi-supervised VAEs also have the invariance, it basically allows you to give the example of object in one orientation and find all the objects like this with the different orientations within the image. So if you can do the content retrieval of your data set. And then the fourth scenario is the case when the number of classes is known, but not the classes themselves. So in this case, we have the approach called the joint VAE. Basically, what the joint VAE tries to do is to take your data, separate it in the number of classes you provide as best as it can, but we kind of have no way to control which data object goes to which class. So if we knew something about the classes, we would, if we had some class labels, we would use semi-supervised VAEs. If we don't have any class labels, but we just know that there is some number of classes, we will use the joint VAEs. Let's see how it works. So first of all, the way it is implemented is basically through the universal VAE approach, when you basically start with the autoencoder, and then you do a little bit of the engineering in the latent space to give the rotation angles, and then you also can class condition it or continuous condition it based on what you want to show. There are other technical details like engineering the skip connections for better reconstruction. So it's kind of maybe not important at this point. But the third thing which is can be added to the VAEs and which is exceptionally important is the fact that we can also impose some physics on the reconstructed objects. And typical example would be that imagine that we use autoencoder to analyze the microscopy data. One of the physical constraints we may have is that the images, is that the boundaries between the different phases should be smooth. We can actually add this type of losses into the system as well. So that's a great way to add the physics to the VAE architectures. Anyway, let's see how it works. So, I mean, as an example of the conditional autoencoders with and without invariances, let's look at the MNIST data set and when we condition the data based on the digit. So in this case, we have a latent space for each of the digits separately. And you can see that if we add a lot of disorder, look what happens. So in this case, the autoencoder tries to disentangle the representation. Rotation is the primary factor of variation. And it turns out that if the objects have the general invariance, the SO2 symmetry group, you will not be able to get a nice picture. So the center of the latent space have a clearly unphysical objects. Physical objects are sitting at the periphery of the latent space. For eights, it's even worse. It's kind of become like a dot with what's not. So if you look with the rotations, then the disentanglement is perfect. So joint VAEs, as I mentioned, they basically try to do the same trick, but in addition, it tries to assign the object to the discrete class. So again, the details of how it's done is not very important for now, except that basically the best way to think about it is that it disentangle rotation translation. It learns the discrete classes. And again, we can add the physics best losses if we want to. And this is example of the joint variational autoencoder of the MNIST dataset. So in this case, you can ask a question, how do I choose the number of classes correctly? That's a very good question. And the answer is essentially by trial and error. That's the only way of doing it. You can do a little bit better than that if you know that the classes are balanced, meaning that you have somehow you know that there is roughly the same number of objects of each class, you just don't know which they are. It's the case for MNIST dataset. That's usually a strong assumption for any real-world experimental scenario. So it rarely is the case that we know that we don't know the number of classes, but we know that no matter what the number of classes is, there is roughly the same number of examples with all of them. So the way you can kind of get a little bit of intuition for that is basically to experiment with a different number of classes. For example, for MNIST dataset, we tried 6, we tried 10, 10 is the right number, and we tried 18, so 18 is too much. So see what happens. If there are 6 classes, then 6s get 1 class for themselves. 1s get 1 class for themselves. 0s got 1 class for themselves. 4s, 9, and 7s kind of share common class, and so is 5, 3s, 2s, and so on. So similarly, the final class is something that is mixed between 5s and 8s. I don't know whether it is true or not, but maybe down the line we will learn how to use the quality of the reconstruction to learn the right number of classes. But to the best of my knowledge, it has not been done, and for the time being, we haven't tried. So that said, you can kind of see that maybe this supposition is correct, because if you try to introduce the right number of classes, you can see that now 6s, 7s, 1s, 0s are kind of okay, but you can still see that 4s and 9s mixed together kind of 4s and 9s here. Here means mixed together. 5s and 8s are kind of close to each other, and so on. So even if you have the right number of classes, it is not necessarily guaranteed that the ground truth labels would be correct. It of course works better than wrong number of classes, but by some margin. So one thing that we can try to do is to introduce definitely more classes that there should be and see whether we can create the clean classes and then kind of do the agglomerative clustering. To some extent it works, but now you can see that, for example, zeros will take 2 classes for themselves. We were successful in separating 6s and 9s, but again, 9 and 4 will mix a little bit. 3 and 5 will mix a little bit. So it works better, but still not perfectly. And then kind of another thing that we can do is to ensemble our autoencoders. So the question is, why would we want to do that? So you know very well that the problem with the many deep learning methods is the out-of-distribution shift. So it seems that one way we can work with the joint autoencoders is to run multiple of them at the same time and then compare the predictions. So it seems to be the case that the clean classes remain more or less stable if we have multiple models in the ensemble, but the case when the classification is imperfect, we have a pretty high uncertainties. So this may be another indicator of the quality of separation. But anyway, that's something that is open for the active research at this time. Now, again, sort of before we go and briefly play with the notebook, let's look at the examples of the practical use of the autoencoders. So I primarily work with them for the spectral and imaging data as the kind of advanced version of the tools like linear dimensionality reduction, clustering, and so on and so forth. Let me show you a few examples of how it works and how to analyze it. So again, this is important because once we discuss how to use VIEs for the experimental data, this creates the platform for use of the deep kernel learning for the active experiment. In some sense, if all the data is already acquired, we can use VIEs. If we want to run the active experiment, we use the deep kernel learning. So it's not exactly an active version of the VIE, but that's a kind of good way to describe it. Now, whenever we apply any machine learning method for the real-world experiment, the first thing that we need to do is to engineer our features. So if you have the microscope and it produces the image, or if you use optical microscopy, or you measure the IV curve or whatever, you need to define what is that you send into the machine learning algorithm. And it turns out that the feature engineering is in some sense as important as the choice of the machine learning architecture, for the very simple reason that feature engineering is one of the ways how we encode the physics in our analysis. For example, if we work with the standard deep convolutional networks, they make the implicit assumption of the continuous translational symmetry. So if we solve the problem of finding the cat in the image, we expect the cat to be found whether it is the top left part of the image or the bottom right of the part of the image. So the DCNNs are supposed to be have continuous translational invariance. So if we work with the data, sometimes we can make a descriptors based on some objects of interest. So for atomically resolved image, the natural object of image is the atoms. So you can find their position. For images, mesoscopically resolution images, we can use the techniques like SIFT, scale invariant feature transform, blob finders, edge finders, whatever. But the choice of your feature finder determines what is that you're going to learn from your analysis. Sometimes we come up with the integrated approaches. So for example, if we take the atomically resolved image and transform it into the atomic coordinates, we basically throw out all the information associated with the contrast within the image. So sometimes we use the atomic position or grain boundary coordinates, whatever, as the anchor points for selection of the patches on the image. But generally, for the time being, the primary type of the image encoding we worked with is patches. So typically, the example of how we can use the autoencoder for experimental analysis is basically the following. We start with the image. We find all the atoms in the image. Can be based on maximum using blob log, DCNN, doesn't matter. Then we create the descriptors, meaning the patches that are centered on individual atoms. Of course, we keep track of what part of the image the patch has come from. And then we basically do the following thing. We send these patches to the autoencoders. Each patch become a collection of the latent variables, and then we plot these latent variables at the positions of the original atoms. So this is typically the trick. So notice that we cannot plot as the 2D maps because our patches are not sampled on the rectangular grid, they are sampled on the atomic positions. So what do we get in this case? So imagine that we look at this image of the two materials together, nickel oxide and LSMO. This is how our patch look like. So we chosen the size, so it is commensurate with the size of the unit cell. And then I'm showing you exactly the same things that I did for the MNIST, but now applied to the image patches. So this is our latent representation. So look what happened here. On the left, you can clearly see that there are 4 bright atoms and the weak central atom. On the right, you can see that now we have a strong central atom, strong 4 atoms around it. So clearly this is centered on these cations, and this is centered on these cations, on these cations. You can also see that if you go from top to bottom, the relative intensity of the central atom start to change. So how does the latent representation look like? So in this case, we looked at the rotation invariant autoencoder. So we with the offsets. So we have 3 latent variables, angle and 2 offsets, which are physically defined. We have 2 latent variables, which is everything else. So look what happens. So this is becoming the angle image. So they represent of the AB type cation. This basically illustrates what is the sublattice it is. But the interesting information is contained in the offsets and the latent 2. So notice that the latent 2 does not have features associated with the atomic periodicity. I mean, there is a little bit, but really not much. So it looks like it separated some factor of variability inside the image. So maybe this is something about the strain fields, maybe it is something else, but this is some form of the continuous autoparameter field that the autoencoder has actually visualized for us. Again, it may be strain, it may be something else, but we of course can analyze strain, but this is physically defined. In this case, we discover the smoothly varying variable from the data only. We also see that, interestingly, one of our channels start to have this horizontal line. So, I mean, for those of you who are familiar with microscopy, this is obviously the non-ideality of the scanning system. And if we can separate it, then we can correct for it. We just make this offset 0, and then we use the generative property of the autoencoder to reconstruct the object without the shear. So we can play more with it. So we can look at the distributions in the latent space. So typically we take the data and superimpose the kernel density estimates. So we see a lot of points, but we see that there are 3 well-defined clusters. And you can clearly see, if we color the image by the cluster labels, it's very clear that one of those is nickel oxide, one is A site, another is B site. You can also make some conclusions about what is the distribution between the clusters. So, for example, this one and this one are connected, this one and this one are connected, but there are no points that are sitting between these 2 clusters. So that gives you some insight in the physics of the system, and it can be some analyzed and some physical conclusion can be derived from. The reason, in fact, why we created the joint autoencoders was exactly to deal with this problem. So rather than dump everything in one latent space, we actually try to separate it into different latent spaces. Interestingly, autoencoders are also exceptionally good in telling us something that we don't know about. So if you take the image of the ideal crystal visualized under the microscope, put it in the find the atoms, create the patches, dump it in the VIE, and look at the result. Looks what happens. So this is latent representation. You don't see much. These are latent angle and the offsets. Again, you don't see much. They're absolutely random. But what's interesting, if we look at the latent 1 and latent 2, you can see a very clear contrast from the left to the right. So, which is pretty much invisible in any other way. So where does it come from? I mean, the electron microscopes have a flyback delay, which is the non-ideality of the scanning. So it turns out that if we look at the single crystal, which doesn't have any factors of variability, we start to detect the non-ideality of the scanning process. Of course, if it had other factors of variability, sometimes VA would be able to separate them, sometimes it will not. But the interesting thing is that it allows us to actually correct for the image non-ideality. Now, an interesting question, can we do this without atom finding? The answer is sometimes. So as a simple example, let's say we have the image of the Bethen ferrite and nickel oxide, same image of NeO, LSO, Mo. So in this case, we don't see it directly, but okay, we can see the substrate, but there are also ferroelectric domains here. In this case, there are two phases, so that one is visible by eye. So what happens if we try to put this data in the normal VIE without atom centering? Our latent distributions are very complicated, and our latent images are also very complicated. So when something is complicated in the latent space, that's actually bad. So it actually kind of takes some time to learn this logic, because we typically think that if there is a lot of details, that's interesting, and if there are very few details, then it is not. When you work with the VIEs, the reverse is true. If you see a lot of details, that means there are complexity of the process that you can visualize, but you don't know what they are. And if the latent distribution is simple, that actually means that you understand what are the factors of variability, and everything else is simple. So it's not what you want to find, it's what is left to find. Let's put it this way. So sometimes we get a pretty good result if we add the translational invariance. So again, this autoencoders require tuning, and it's a separate story of what it takes to tune them. But once you've done it, it actually works remarkably well. So notice that if we add the translational invariance, so the shift VIEs, in this case, our latent representations are nice. Our latent distribution have a well-defined maxima, and you can clearly see that our image shows the ferroelectric domains and the three maxima corresponding to one ferroelectric state, another ferroelectric state, and substrate. And for the two-phase material, there are only two maxima as well. So that's actually super interesting. And of course, the reason why we're interested in it is because it's much in atomically resolved images. We apply this methods, and sometimes we can discover atoms, but in most experimental scenarios, we don't know. Most experimental scenarios don't have the well-defined key points. So there are other things we can do with the VIEs. For example, imagine that we explore a system like graphene or any disordered material. So in this case, we can get an image, we can use the deep convolutional network to segment it, meaning find each atom of carbon and some of the atoms of silicon. So we also use the masking in order to ignore the kind of this large disordered region. And if we take this data and create the patches centered of each atom, send it to the VIE, and then visualize the data, you can see that this is angle map. So basically, angle in this case means the orientation of the three neighbors in the overall plane of the image. And this is the latent variable corresponding one of the other latent variables. And you can instantly see that in this case, you can clearly build the relationship between the value of the latent variable and the degree of crystallinity. So if the material is crystalline, the latent variable is 1. If it is not crystalline, latent variable is lower. So basically, each type of possible chemical neighborhood in graphene becomes encoded as the latent variable. So we sort of put a number on disorder, if you will. And this is also actually exceptionally illustrative. So this is the latent representation, and you see how the autoencoder learns to recognize the structures. And this is the movie of the graphene evolution when the colors are actually the latent variable. So you can see the dynamics. You can easily visualize how the ideal and non-ideal parts of the graphene move around. So it's kind of pretty cool. It can be done even more interesting if we focus on reconstruction of the data, so in the VIE. So in this case, very often our latent space will have objects that look like the textbook example of the organic molecules. So at the first glance, it's nothing special, right? We expect the objects to look like organic molecules. But the thing is that that's what we know. The autoencoder doesn't know that. So if you think about what happens if you analyze the data using autoencoder, you actually use the unsupervised machine learning to reconstruct the chemistry of the system. So you start with the raw observation, you transform it into the segmented data set. So when we do this, we just postulate that atom exists discrete and have a known shape. So that's what the DCNN, this is a set of principles that the DCNN decoding uses. And then we try to analyze this data using the VIE. And basically what it means is that we say that there are structures are parsimonious in nature, meaning that there is a large by finite number of the similar structure, not the infinite number. And it turns out that we can then discover what the structures are. And our reconstructions are either ideal graphene or so 3 6-member rings, or 5 and 7-member ring, or 2 7-member ring and the 5-member ring, and so on. So this is kind of one of the common misconceptions with the application of machine learning in physical problems, because sometimes we get an answer which is trivial and we say that it is not interesting. This is a wrong way of looking at things, because it is not trivial, it is human explainable. So if we understand the answer, it means that it makes sense for us. Sometimes we get answers which are not immediately understandable. And in this case, it means that the algorithms still work, we just don't understand the answer. So if you want to be a kind of cynical about it, one way to say it is that we cannot discover new physics by machine learning, because if we understand the answer, then it is not new. And if we don't understand the answer, then it is not physics. This, of course, being a little bit negative. Practically, there is a narrow interval between something that's obvious and something that is not understandable. So then we actually discover something new. Let me show you a few examples when it worked. So this is, let's bypass this part. So, and this is the last example, no, not the last example, but one of the last examples of using the VIEs to understand the dynamics of the domain walls. So we can visualize how the domain wall evolves using scanning probe microscope. We can use the filtering to find the 180-degree domain walls. That's just very simple, just canny filter. We can use the deep convolutional networks to find the ferroelastic walls. That's a little bit more complicated, so it takes a little bit effort to clean the data and train the network and whatever. But once we are done, we would be able to get a picture of the ferroelastic walls. And then we can take the objects, take the points that lay on the domain wall, take the image patches around this domain wall, and apply the VA approach. And then our latent space actually contains the information of what are the possible structures of the domain wall. So here you have a straight domain walls. Here you clearly see the kind of corners of the domain. So if you see the here you see this kind of needle domains that grow when the polarization switches. So this part of the latent space contains the information of these needle domains. This is, for example, the parts of the ferroelectric domain structure that correspond to small domain periodicity. And then kind of question becomes, can we understand here? Yes, if we come up with our own physical criteria, we can say that, for example, we can count the distribution of the domain walls in the latent space. We can analyze the degree of switching. We can analyze the average wall curvature. And you can basically see that degree of switching has a uniform smooth distribution in latent space. Domain wall count is okay. Curvature is not okay, presumably because we don't have enough data. And then there are many other ways we can extend it. So with this logic, for example, it's very easy to extend this analysis to probe the time dynamics. In this case, all we have to do is to choose the position of the domain wall at one time and create our descriptor in the time plus delta t. Then we encode the information of the domain dynamics, and we can analyze it, explore it in different ways, and kind of get the similar type of insights. And we typically always have a very beautiful visualizations of the dynamics in the latent space. So this is example of how the domain wall moves and how the latent variable changes across the domain wall when it moves forward. So slightly more complex example of the insights when we learn from the VIEs is when we have different type of objects. So let's say we have two types of domain walls, the 180 degrees and the non-180 degrees. So we can create the objects for our VIEs which have two layers, one layer corresponding to the 180 degree, the second layer corresponding to not 180 degree. And then we can create the latent encoding. And at the first glance, something like this looks totally non-understandable. So what does it tell us? But actually, if you think about it a little bit carefully, you can start to identify the physics mechanism based on the way the objects are represented in the latent space. So for example, here you can see that ferroelectric and ferroelastic walls are basically coincide. So what it tells you is that ferroelectric wall cannot move without ferroelastic wall, vice versa, which means that this is the region when there is a strong pinning. So if you're in this part of the latent space, you can see that ferroelectric wall is kind of more like a straight line, but the color is not uniform. So generally it's bright in the center and weaker at the edges, and there is no visible blue color. So what that tells you is that if you fix the domain wall in the center, the positions of the edges close to the edges of the scan would be changing, which means that the wall kind of undergoes this type of libration dynamics. And basically it tells me if there is no ferroelastic wall, the ferroelectric domain wall is very mobile. And the way you interpret the data here is essentially this is coming from these regions where the ferroelectric wall is pinned not by a single ferroelastic wall, but by the multiple ferroelastic walls perpendicular to it. So notice that this analysis is highly domain specific and you really need to understand your material and what goes on, but it's possible, and then it puts numbers on that. So you can quantify this behavior, spinning efficiency, wall coincidence, gradients, and so on. Now, the final thing that I want to mention before I show you the collab is that, strictly speaking, we can extend the concept of the variational autoencoder into the encoder-decoder. So what does it mean? So from the point of view of the neural network architecture, that means that if we take some data as an input and encode it to the latent vector, we can do the deconvolution into a different data object. That's it. So that's why it's encoder-decoder. Of course, for that, we need to have a pairs of the inputs and the outputs. So they have to be paired. So from the point of view of material science, all of you have heard the expression of the structure-property relationship. So in material science, a structure-property relationship. In, let's say, medical chemistry or biology, it's quasi-quantitative structure-activity relationships. So different fields have different different words for that. So in imaging, this would be the relationship between the local structure and local spectroscopy. For scanning probe microscopy, it can be local spectrum, local structure. For electron microscopy, it can be local structure and local ILS, or local structure of 4D stem. So basically, it is some paired data. And it turns out that we can use this encoder-decoder architectures as the generative model to build the relationship between structure and properties. So kind of jumping forward a little bit, deep kernel learning is how you build this relationship as an active learning and how you structure your experiment to do it as fast as possible. Encoders, decoders is how you do it when the data is already acquired and you don't need to do active learning. So these are a few examples when we did it for PFM data. So this is our input, this is our output, and you compare the prediction and the ground truth. So they're very close. This is another example when we do the same thing for the structure property relationship in the plasmonic nanoparticles. So this is our input, the structural image. This is the prediction and compare it to the ground truth. So you can see that we can predict the plasmonic spectra based on the local configuration remarkably well. Interestingly, it almost works in the opposite way. If you take the spectrum and try to predict the structure, you will not be able to get the details right, because there are a large number of invariances here. But generally, you can reconstruct the relevant features. For example, if this is the prediction, this is how the ground truth look like. So there is a missing corner. This is the case when there is an edge, both here and here. So it kind of works reasonably good. And there are, of course, many other ways to make it better. For example, you can go from the structure like encoder-decoder to the structure like a dual encoder. So you basically have imagine that you have a data set when you have the SEM images that you get with SEM, and you have the hyperspectral data set that you get from the far field or hyperspectral optical camera. So you have a relationship between structure and spectrum. So the way you build the dual VIE is you take these pairs of data, you encode them by different encoders into the common Latin space, and then you decode them back. So all these 4 elements, 2 encoders, 2 decoders, are trained jointly, and you can impose some degree of connection into the Latin space objects, are they rigid or not so rigid. And as a result, you get beautiful latent manifold representations. So now obviously you have 2, and you get an option of predicting the structure based on the far field optical image. So this is actually kind of important, because in order to get a SEM image, you need to kind of spend some time and effort. It's actually takes some time to do it manually. The far field optical images are much easier to take. You just take the image of the object and find the bright blobs. So look how things work. So this is optical image. This is the ground truth corresponding to these 8 particles. And these are the predictions. So for trimers, we got the predictions almost right. The monomers, we get the predictions exactly right. For 4 particles, I mean, it's a different 4 particle, right? Because we deal with the, obviously we create the different train and test data, but still it got it close to reality. 5 didn't pan out. For 2, sometimes it misidentifies 3, sometimes 2 and 2 are correct. But generally, if we build our accuracy matrix, is actually not that bad. So as I said, autoencoders is almost infinite topic. I've shown you a few examples focusing on the primary concept behind that, but let's play a little bit with the notebook. So we are not going to go through the notebooks for all types of the autoencoders because it will take forever. So let's look at the one that shows the classical VIEs, and then all the others we will I will put them on the GitHub, and you would be able to go them at length. So they're written in such way as to be self-explanatory. So again, the reason why we are doing it this way, because autoencoders itself can be about 5 independent lectures to dig to them at some level of detail, from different ways they can be configured to different ways how we can create a data set, to different ways how we can play with the physical constraints and so on and so forth. So anyway, so now this notebook is already on the GitHub. So let's just look through the main elements of this notebook. So I'm not going to run it, but I checked it this morning, so it should be fully operational. So the first thing we install is the Cornea. So Cornea and the Max's Pyravet module. So Cornea is basically a library that allows you to augment the data. So it just makes your data generation easier. Then we do the imports. So we import the Pyravet, which is this library for the VAs. We import Cornea. We import the CV2, the torch, NumPy, Matplotlib, lips, or the usual parameters. So then what we do is we create the helper function that allow us to apply the transformations to the data set. So as you can figure out, we start with the resizing function. So to make them all the images at the same size using the cubic spline interpolation. We read some objects. So this is our cards. We normalize them and we return the normalized objects. And then we create the transformation function that does the transformation. So what this function does, it takes a list of cards and some parameters, and then it basically starts to apply the transforms. So what this line means is that it the number of arguments that can be passed of the function can be variable. So what the function tries to do is to decode this string of the optional arguments and see if we provide the values of angles, translation, and shear. So basically think it about the optional parameters. So then we create the number of samples, and basically we create multiple objects. So we go from 1 example to 3,000 examples. Then we concatenate them. Now this is the interesting part. So what we do here is we use our, what we pass to the function is the values of angles, translations, and shear. What these values are used for is to create a random uniform distribution. So if we pass the value of angle to being 10, we create the uniform distribution from -a to a. If we put that, give the translation vector as 2, our translation will have a uniform distribution from -t to t. If we use shear as 11, then the shear distribution would be uniform from -11 to 11. So if you want to play with this code more, you can easily change this distribution to being Gaussian, or kind of, again, choose whatever you want. And then what we do is we just apply these transforms to our original card data set. And generally, we just return the values of the array of the images, and then the ground truth labels, angles, translations, and shears. So this is the card object. These are the ground truth labels. We also have the function to plot the manifold, which is, you'll see how it works down the line. So then we import the cards data set. So the cards data set is just these 4 images. So the clubs, pikes, hearts, and diamonds. And then what we do is then we create the 4 data sets that I've shown you in the first part of the presentation. So as you can see that we have data sets 1, 2, 3, 4, corresponding labels, angles, translation, and shears. And all of this are formed by this transformation function of the original cards with these parameters: angle, translation, shear, number of samples. So if you run the collab without the GPU, one of the way to make things faster is, rather than making 3,000 examples, to make 300. So your quality of the latent distribution would be slightly lower, but the same features would be there. So this is how the cards look like. So then the way we make things work, we create the object called train loader. Basically, this is a way to not keep all the data in memory, but keep it on storage and then give it to the network in batches so it kind of trains effectively. So if we work with a small data set, we don't need it. We can just pass the full data set to the network. If we have a lot of data and we want to avoid our Colab crashing, then we use the train loader. So if we choose the first train loader, and so here you define what of the data sets you want to analyze. So in this case, I say that I want to take a fourth train loader, and I want to take the fourth list, meaning corresponding the strong angle and shear disorder. It's obviously important to have the same number here and here, because otherwise your labels come from one data set and the images come from the different data set, so that's kind of awkward. But then this is how the training part look like. So as many things that Maxim have developed, or so what is called a good Python style, your active actual code is actually very short. So what you do is you define the dimensionality of your data. So the network need to know what do the inputs look like. Then you initialize the probabilistic VA model. So these are the parameters that we can play with. And this is something that I encourage you to experiment, because this is exactly the part that is interesting. So we can say that we don't have any invariances, then it is simple vanilla VA, so no invariances whatsoever. We can set the invariances to be R, as is done now. That means that we enforce rotational invariance. We can set it to T, that we enforce translational invariance, so we can say R and T, then it is both rotation and translation. And then the way we apply this really powerful tool is basically just one line of code. So we create a model which has the input dimension, so the size of our object. Obviously, if we want to apply it to the spectrum, then the size of our object would be 48, comma. It would be one-dimensional. So this is our latent dimension. So this is how many latent variables. We typically use 2. Obviously, it's a good idea to experiment with other numbers of latent dimension. So we get a little bit of say in how we can configure the latent variables. So we can configure the internal structure of the encoder and decoder if we want to. So you can use it as it is, or you can just drop this line, and then you provide the invariances. So after that, we initialize the trainer, and then we train the network 100 times. So the output of the training is the loss. Obviously, what we do is we look at how this loss behaves, and generally, if the loss starts to saturate, we generally can stop the process. So in my experience, if you train the normal VAs, the loss typically smoothly decays and stabilizes. For joint VAs and more complex architectures, it can stabilize and then it can start to train again. So there you may prefer to train longer. So how do we visualize the results? So very simple. If we want to visualize the original data set, we basically use this help function, which basically creates this type of representation of the randomly chosen samples of the original data set. So if you can play with this code, is actually straightforward. All we do is we choose randomly several objects from the car data set, and then we visualize them. So this is our latent representation. So in this case, let's see if my notebook is still active. No, it will not be active, so it's not going to work. Sorry. So I will need to retrain it. But basically, what it allows you to do is to show the manifold. In this case, I've chosen 100 objects, but can be small, more can be less. More would be difficult to understand what goes on. So then we can visualize the latent distributions. So the way we visualize the latent distribution is that we take our data set, then we encode it. So RYE encode is encoding function, and then we get the mean and dispersion values. So mean is the latent variable, dispersion is its uncertainty. So what uncertainty is good for is almost unexplored by now. So that's something that can be interesting direction to explore for the curious mind. So notice that the number of the latent variables depend on what type of the VAE you have chosen. So for example, if we choose the normal VAE, we will have two latent variables. If we choose the rotation invariant VAE, we will have the rotation and two latent variables. If we have the rotation translation, then we have rotation, first translation component, second translation component, and additional to then our latent vector is 5-dimensional. So we have access to all these components. We can choose which one we want to visualize. So when we use z-mean -1 and -2, that means that we take the true latent variables because we count from the end. If we want to look at the rotational translation, we choose first or first, second, and third, and so on. And then we get a representation of these images, which you saw in the presentation. And in principle, we can just kind of play with them as much as you want. And then you can kind of visualize the angle distribution, which in this case is pretty much disentangled, translations, and so on and so forth. And finally, this is the example of the angular encoding, again, as in the image. So this is the example of the notebook for the classical VAE and the rotational VAE. There would be 3 more notebooks for the conditional, semi-supervised, and joint VAEs. So let me just kind of, for the last 5 minutes or show the example of the VAE for the semi-supervised one, because that one is relatively more complex. Again, the logic here would be exactly the same. So you download the same libraries, you create exactly the same helper functions, you create exactly the same data loaders. The only difference is that in this case, you create a more complex data loader corresponding to unsupervised, supervised, and validation data set. So if you go through the examples, you can see that in this case, we have a slightly more complex data structure because we have features and some of the targets. But it should be pretty self-explanatory. And again, I run it this morning, and it works remarkably well. So you would be able to go through the collab and see how it works and kind of how the outputs look like, using the classical confusion matrix to see whether the label propagation was successful or not. So kind of play with it, and let's stop at this point, and let me know if you have any questions that I can answer.
I do have one question. So, like compared to the VAE method, in the RVAE method, we are introducing like more parameters to fit, right? Like, do we concern about the overfitting, or do we need like more data to train this model?
Surprisingly not. So I'm sure that there are modes in which the RVAE can fail. So, but these modes are very different from the supervised learning. So we have overfitting in the supervised learning if we have too complex network and too little data, for example. So that's kind of correct. The unsupervised methods work very differently. So once we define the rotation vector, the latent variable corresponding to rotation, it is basically rigidly defined. We cannot overfit on that. We can find it incorrectly because we don't have enough objects, or because the same object looks the same under different orientation. So for example, if you create the data set when you have the rhombuses and your your rotational disorder is more than 90 degrees, then you kind of create the degenerate case. The same object will look the same if you rotate it by 30 degrees, say, and by 120 degrees. So in this case, the latent distribution will split into the several groups. It's actually very visible when you have the ground truth, and almost impossible to identify if you don't have the ground truth. But they don't overfit. And another very interesting thing is that generally when we apply machine learning, we always think that we need to have more examples than dimensionality of the data. So for example, if you analyze the MNIST data set, the dimensionality of your data is 756, and you have 50,000 examples. So you have much more data than the dimensionality of a single data point. The thing which is very, very interesting about the autoencoders is that they produce useful results even in the cases when the number of examples is much smaller than dimensionality of the data. For example, for the plasmonic nanostructures that I've shown you, the dimensionality of the data was something like 4,000 or something. So it was roughly maybe 60 by 60 data points or something like this. So 3,600 to be more precise. But we were able to train the network based on something like 200 examples. So the number of data points was considerably smaller than the dimensionality of the data set. So we can speculate that it works because the VIE sort of does the internal augmentation of the data. So we had to increase the training lengths by basically order of magnitude, but that's a speculation. So I'm not that much of the expert in the mechanics of the training of this type of models. It's sort of a science by itself, but practically it works. So we didn't go to the extreme of using something like 5 data sets or what's not, but it works for reasonable cases. What is also very important is that once we get to the deep kernel learning in the next lecture, we will see that the same advantage falls to the deep kernel learning, and it's even more pronounced. So what I mean by that is that if we use the normal Bayesian optimization methods in a reasonably kind of moderate dimensional cases, 4 or 5 whatever dimensions, they kind of work, but they really do not save that much data sets. So for all the practical imaging problems that we had, Bayesian optimization allowed us to use 3 times less data points, but not 10 times less data points, which is absolutely not enough. So a factor of 3 is okay, and it matters in a sense that if your experiment takes a day and not 3 days, that would be a win. But the problem is that once you go from the normal sampling on the grid to more complex sampling proposed by the Bayesian optimization, your experiment becomes more complex. So you cannot just go from one part of the image to the other part of the image and come back, because you always will have some distortion. So if you win by a factor of 3 in the number of data points, but you lose by unknown amount and complexity of experiment, it really stops being worth it. If we use the deep kernel learning, then our win can easily be a factor of 30 and to factor of 100, which is actually not a small number. Of course, we don't have any mathematical framework which explains why it would be the case. It is just a set of observation for considerable number of model experiments, but still it's a phenomenological finding. But it also works in the practical experimental setting. So there should be something that gives you this type of benefit. And as I said, it probably is related to the capability of the VAEs to train well and find the latent representation using a very small amount of data. And that probably in turn relates to the fact that physics is ultimately parsimonious. So the number of real physical numbers of variability is actually very small in any system. The problem is that we don't have access to those factors of variability. We have access to their large dimensional representations like images or spectra. So the autoencoders implicitly find the slow dimensional factors of variability. not exactly, but in some combination corresponding to the latent variables.
Got it. Yeah, thanks.
Any more questions? Okay, then if not, then I encourage you to play with the notebooks on the GitHub. So there would be quite a few of them. So that would already be a considerable effort. Keep in mind that these notebooks are only for the cars dataset. So if any of you are interested, I have the matching notebooks for imaging datasets, for example, graphene or bismuth ferrite, and spectroscopic datasets like STM datasets or AFM. So that can be a lot. But the car dataset is a good one to build the intuition for how it works. Other datasets, other notebooks are basically example of how it works for the real world scenarios. And they should be easy enough to configure to the data that you have of your own if you're interested. But as I said, this by itself would be a set of lectures and the hands-on exercises. The reason why we look at it in this short introduction into the automated experiment is because it introduced the primary concept that we absolutely need to implement the deep kernel learning methods. Sound good? Okay, so if no more questions, then thank you for coming, and I'm off to the conference. So talk to you next week.